All right, how are we feeling? Ready to start going over it? Okay. All right. So let us start with the first one. Yes or no?
No.
No. Wait for the animation. It's no. And why is it no? Because of 13, right? It shouldn't be there. Okay, what about the second one?
No.
Yes. Yes.
Nah, that's crazy. I thought it had to have children. That's crazy.
Technically, yes. Even if we're empty, like technically, yes. Because, you know. All right, how about the third one?
Yes. Yes.
Yeah, that one's right. Okay, let's do this one. So we start, and let me actually, I'm gonna make it a little bit bigger. So 54, where does it go?
To the right of 49.
Right, there we go. How about 24?
To the right of 15.
And 51? Yep. 11? And 48.
To the left of 51.
Right there. Yeah. So it will come down, right? It's bigger than 42, but it's less than 49.
But can it not? Could it not go on the left of 51?
It can't get down there because it's got 49.
All right.
Yeah. Okay. So I think this summarizes the points. So if you will add up your points and put it in the top for me. Don't forget to add one for your name, and also put your name on it if you want any points. But
So how many points should it be total? So
9.
With the name?
Yeah, with your name. Yeah, 9. Yes.
Could it with a 54 be? Can you put 51 and then put 54 to the right?
So you could if 51 were first in this list. So if you're going in order, like you add 54, then you add 24, then you add 51. So that's part of it. Yeah.
So what's 7 out of 9?
I don't know. Like a little bit less than 70. I don't know.
A little bit less than 7. No, 77. Yes, 77.
77, a little bit more than 7. Okay. If you will pass them all kind of inwards, I will pick them up, I will scan them and put them on canvas for you. Okay, was that good or bad or? Looks pretty good. The second one, why is it correct? It's just one node, so it doesn't. It follows the properties of the binary search tree. Yeah.
I thought it doesn't have to have children.
It doesn't have to have children. That's right. Yeah. Okay, so let us start with where we are. We just did this quiz Wednesday. Today we are going to look at writing some code for binary search trees. I think we will probably not finish that today, so we'll probably do a little bit more of that on Friday, and then we'll move to AVL trees.
So when we write in that code, is this the type of code we would use on our project?
Yes, so this, you will have challenge number 3, which comes after the stacks and queues, which is challenge number 2. So challenge number 3 will use a binary search tree, and we will write the code that you will start with for that. And we'll start writing that today. So if you remember last time, we talked about binary search trees. We went through how to insert, how to search, how to delete, with the most interesting being deleting a node, like the root node or something in this case, where you had choices you could make. And so here's the binary search tree property, which just is that the value of the left child is always less than the value of the parent, and the right child is always greater than the parent. And so it's your example of a valid tree and then an invalid tree. All right, so we're going to build our binary search tree in C++. And to do that, we are going to be writing a number of files for this project. So the first one we're going to use is node, which you remember we wrote a node class for linked list. So this will be very similar but different. It'll have the right and left rather than like next and prev. So this just is to break down the files that we'll be creating as part of this project. So for your node class, which we'll make objects of, we'll have a header file for node, and we'll have a C++ file for node. Similarly, for the binary search tree, we're just going to call it BST like this, and we'll have a header file for BST, a C++ file for BST, and then we're going to have a test bst.cpp where we'll have our main function to actually test things. So there are, there are a lot of ways you could do this. We're going to do this in the way that kind of the TAs expect it to be done for challenge 3. And that's not necessarily saying that that's the best way. It's certainly not the only way. And it's probably not exactly the way that I would go about it. But it's a fine way of doing it, and we'll learn a few things as we go through it. So this is the header file that you will need for the programming challenge. So this is the binary search tree class, and these are the methods that need to be there. And these are the full method signatures or function signatures that need to be supported. So first what you'll notice is we've got kind of an even divide here between private and public methods. And if you don't remember a lot about the ideas of private versus public in a class, the thing to remember is that in general, private methods, private variables are used within the class itself. So within the functions we write for the class, we can access those, we can call those, we can use them all we want. The public set of variables and functions are used by whoever's using the class itself. So in our case, it'll be our test BST program that we're writing. We will call only the public methods from that file. And the idea is kind of what we have with any object-oriented approach is that we want to be able to take and seal off our implementation from whatever the end using client is. So it's kind of like if you want to interact with like a web service or something, like say you want to integrate with, I don't know, like Ring doorbell or something, right? They have an API, right? And they give you an API and it's full of like headers, inputs and outputs. What did you supply? What does it give back? That kind of thing. And that's exactly what we're doing here. And so the public ones being kind of what we could give to anyone and say you can use. The private ones being things that we use internally. And maybe if we were developing a real product, those might change. Then we wouldn't have to worry about it breaking somebody else's code, because as long as they use the public ones and we support the public things, we're good. So the main difference for us, why we're doing this here, you'll see that for insert, remove, and destroy, we use a recursive approach, kind of how we talked about these different methods when we were talking about them with pseudocode abstractly. And because of that, like the public method for insert, right, we're just doing integer data here as our nodes. It just takes in the integer you want to add, right? That makes sense. If you say, I just want to make a tree and I want to start adding integers, that's all you need to do. The private method takes in a node plus that data. And so that lets us pick where in the tree we want to start. And the client using it doesn't really need to worry about that. And we'll see that what happens for us is all we do is we specify the root node as being the start. There are some things here that are kind of unfortunate in terms of not being super relevant to data structures, but being very much a C++ thing that can be a little bit confusing. So if you kind of flip back in your mind, early on we talked about pointers, we talked about references. We did not talk about something like this, where you can see we've got a pointer to a reference. So I'll let you mind think about that for a while. The reason that we're doing this, and the pumpkin is because Halloween is coming. What are the odds that we get this scary code right when it turns to October? But so a pointer to a reference, the reason we're doing this is so that we can have like a little bit of convenience and set a variable from inside a method when we're doing things recursively. Don't get too worried about this right now. We'll talk about it as we implement it, and I'll try to remind you what it means, because it's a little bit like you've kind of got to think through it, and so it can be hard to keep in your mind like what exactly the meaning of that is when you glance at it. Again, if you're like using C++ every day and doing this, it's no problem. But I think a lot of us use other languages probably more, and maybe this is not just fresh in our mind. So, but don't worry about it. We will go through it as we build this. Okay, so the methods that we're going to support publicly: insert, remove, find, and then our three traversal methods. Also something, and I think you probably saw this in your linked list challenge, taking this OStream as a variable into the parameter, and so that was just to be able to pass cout in as a parameter. Again, not particularly necessary, but that is what kind of the course-wide everyone is doing, so we will support that, and it's not a problem. It's easy. Cout is a type OStream, and you can pass it in and use it, just like anything else. Okay, so let's start with the node class. I'm going to jump over here, and I'm going to make this bigger. Okay, so I'm just going to create a new file here, and I'm just in a folder called in class, and there's nothing in here. First thing I'm going to do is create node.h. And so within this folder that I'm working in, this is in my terminal, you can see all we've got is node.h right now. So we will start off writing our node header file. And so if you remember, we always kind of do this if not defined, then defined, and you can pick really anything here, but the tradition is just to do node h like that, define
So
node h.
for this demo, will you give us anything?
Yeah, you'll get all of this code.
Okay.
So we're going to write it together in class, but I will post it all in complete form. So you don't worry too much about, like, you don't need to necessarily like code this at the same time I'm coding it. You don't need to take detailed notes or anything. Just kind of.
So what will we have to change in the demo?
So in your demo, I'm not sure, because so we change every semester. We kind of change them a little bit, and I honestly cannot remember what we decided on that one. It's similar to the other, so it's not a big change. It's going to be something with one of the functions basically, but we'll talk about how to implement that in class as well. Like, we'll go through it. You'll know how to do it, and you'll just have to
Remember how to do it
right. Yeah.
in the moment.
Yes. Okay, so we're writing our node header file, and we put this if not defined, then we define. And if you remember, this is just a preprocessor directive, and so it just helps us because we might include this file in multiple files. It helps the compiler as it comes through make sure that it only includes it once, and that that is all that this is about. So I'm also going to include IOStream here, and I'm going to use a standard namespace. And then I'm going to start my class node, and we're just going to have some public variables. As you can see, okay, so Copilot is on right now. I'm just letting that hang out so you can see that if you want to know, and you can see that it is trying to predict for me what I want to write, and it's pretty close. But we'll kind of just go ahead and say, so each node will have a data field, right? And that's just going to be an integer in our case. So we can make this just a little bit bigger. Okay. And then we're going to have a node to our left, because we're in a tree, we have a left child, and that will be a pointer to another node. And then we will have a node to the right, so that'll be our right child. And so just like we did with linked list, in this header file, I'm going to go ahead and define some constructors for nodes since it's such a basic little class. I'm just going to do a default constructor, so that's just node uppercase with nothing in the parentheses. And I'm going to use this shorthand to set the data variable to 0, and then I'll set my left to be null and my right to be null as well. And so that's just a nice default constructor for us. If we make a new node and we don't pass anything in, it just sets everything, sets the data to 0 and the 2 pointers to null, which is what we would want. So then I'll make another constructor which just takes in a integer that is the data that we want. And in a similar way, I will set left and right to null still, and I'll set data to data. Okay, and so there is one extra method that we want to add into our null, or into our node class, not our null class. And that is not this, but it is a degree function. So we're going to make a function called degree, and it's just going to return an integer, and it's going to be the degree of the node. And so if you remember, a degree of a node is how many children it has in the case of the binary search tree. And so this will be helpful for us because remember when we delete things, if we have one child, we do it one way. If we have 2 children, we do it a different way. So this is a convenience method for doing that. Okay, so I've written that. I'm going to close this class out down here at the bottom and put a semicolon. And so now we've got our node.h. Next, I'm going to go ahead and add in node.cpp. And the only thing I'm going to do in node.cpp is I'm going to write that degree function that we specified. And so we could do this in the header file. And this is a matter of like what, kind of your style practice here. I'm going to break it up because in general, I think we need to practice over and over the idea of having many, many files that compose our project so that we don't get too stuck in trying to put it all in one file. It may not be a big deal for our examples because they're small, but as you start to work on actual things that are quite large and that have teams of people working on them, this will be the default, right? You're going to have lots of files with lots of different things. Okay, so in this file, all we're going to do is define the degree function. And again, you can see the AI is predicting that that's probably what I want to write, and it's kind of close. So how many of you have used like Copilot or an AI as you code? Not saying for class or anything, but just in general. Have you tried that? Some? A little bit? Okay. Good experiences? Kind of in the middle? Yeah. So, yeah. I do recommend that you try it. It can be really, really helpful, and it can be kind of harmful. And I think once you get like a rhythm with it, then it really does help always because you know when to go with it and when not to. But it's kind of just like a fancy autocomplete in a lot of cases, and it can be helpful. Okay. So we need to know how many children are in this node. And so what I'm going to do is I'm just going to make a count, and I'm going to say there's 0 to start with. And then, if you remember, we have a left pointer and a right pointer. And so if that left pointer is not null, that's one child, so I'll add 1 to my count. And then, in a similar way, if my right counter, or my right pointer is not null, that's another child, so I have 2 children. So now I've added 1, 2 to my count of children, and then I'm just going to return count. And so that's the whole degree function there, right, for a node. And that will give you this number 0, 1, or 2 as to how many children the node has at that time. And so that will be useful for us. So let's go ahead and create our test BST.cpp file. And this will just be our main file where we test everything. So I'm going to include IOStream, and I'm going to use the standard namespace, and then I'm going to just write a main method, and then just going to put that in. And I kind of like to get our main file set up early in the project so that we can compile against it and test this kind of thing. So I'm going to go ahead and go over to my terminal to compile this. And so if we take a look at what's in this directory, right, we've got our node.h, our node.cpp, and our test.bst. Now, I'm not going to be using node directly in this test file, but for the time being, I will include it just so we can see that it compiles. And I want to compile these all. And so for me, I'm going to do it this way. So I'm using G++ here for my compiler. I'm passing in this flag of std equals C++ 17, and that's just telling the compiler I want to use the C++ 17 standard, 2017, and that gives me support for things like null pointer. So if you have a really old standard that you're using, it may not have null pointer, it may complain about that. So that's the only flag I'm going to pass in there. There are a ton of flags that you could pass in to your compiler. And you should definitely take an opportunity to look at kind of like the documentation of the compiler. You'll find that surprisingly all of these things are very well documented. And you can often find the answer to your question in that documentation, just like you can searching. Okay, so we're going to compile our test BST. And then we also want to include our node.cpp file. And so I'll run the compiler, and I didn't get any errors. If I look in my folder, you'll see that I have a.out. It's just the default name that we get when we compile something. So I'll do /a.out to run it, and we get our little print message that just says the test file is running. So that's good. It's good to know that what we've done so far has not broken anything. There's nothing to fix yet in terms of that. Okay, so let's move on and let's go to our BST, our binary search tree header. So I'll do bst.h. And because we know it's going to be, it's required by the assignment to be a certain way, I'm not going to make us type all of that out. We're just going to go ahead and copy and paste that in here. And we'll kind of just talk through a few elements of it. So you can see that I've done the if not defined, define BST at h, just like we do with any header file. I'm including OStream because we're using those output stream parameters for cout to pass in. And I'm including my node file that I just wrote so that we have access to that. I'm also using the standard namespace, and this just helps me notationally, so I don't have to write std::ostream when I use that. I can just write ostream shorthand, and it'll show up. It'll work. So these are all of the functions that we talked about when we were looking at slides, and these are all of the ones that will be on the programming challenge that we'll need to support. And so they are all exactly the same. We'll go ahead and just save that. And now I'm going to create the C++ file for this. So bst.cpp. Okay. And for this, we're going to start in this file just defining these functions that we declared in the header file. So we're going to do the actual implementation here. And I'm kind of going to just go in the order of doing the private version first and then the public version, because the public version is actually very short compared to the private version. So the first thing I'm going to do is I'm going to include my bst.h file, and then I'm going to start writing the methods. Now you can see the AI is suggesting that I might want to write this destructor first. I don't want to do that, so I'm just going to ignore it. And so the first thing I'm going to write is the private insert function. And so there you go. There's another example of kind of, if you are coding with the AI, it uses context pretty well. So now that I've just put a comment there, right, it's updated its context, it has a good idea of what I'm wanting to do here, right? So it's suggesting something that's probably pretty close, if not exactly what I want. But we'll go through it. And so I do want just kind of this first part I'm going to grab. So this is just our function header, just as it was in the header file. So when we're inserting a node, the first thing we're going to do is we're going to check and see, because we're doing this recursively, if the node pointer that comes in is null, then that means that's where we want to add this node. And this is exactly why we do this trick with the pointer to a reference, because we want to actually be able to set that value. So let me Copilot doesn't want to turn off. Okay, I'm going to turn off Copilot just because it's being very annoying or it may be distracting. So first thing we're going to do is we're going to check and see if the node we're at is the null pointer. Right. So if that's the case, then what we want to do is we're going to set that node to be a new node with our data in it. And the only reason we can do this is because it is a pointer to a reference. So we're actually able to set it to a new object here. So just like that, we create the new node here with our data, and then we go ahead and set that node to be that, and then we're done here. So I'm just going to return true since we're returning a Boolean. Okay, so that's kind of the base case of we're inserting an element, and we have to tell this function where we're starting in the tree. And so just imagine we've got nothing in the tree, the root's null, say we've passed that in, it's null, and so we're going to put it at the root to start with. So now kind of think of a different scenario. Imagine we've got a tree, it's got a lot of stuff in it. So we come through here and we pass in the root node, right? And it's not null. Okay. So now we need to kind of follow our principles of a binary search tree. Like, where should we put this thing, right? We've got to bounce down the tree according to those rules. So what should we do?
Check to see if the data is greater or less than a node.
Right. So we're at a node, and it's got data, and then we've got data we want to add. So we can compare those and decide which way to go, right? So let's just start by saying if that data is, sorry, you guys able to see this okay? Okay. If that data is less than the node that we're currently at, it's data. So we access it just like that, right? And so that's just saying if the new data is less than the current node's data, then which direction do we want to go? Left, right? And so the way we can do that kind of in this recursive format is to say we're just going to return, and we're going to return a call to insert, which is the function we're in right now. And we're going to call it with the left node as the entry point and our same data as the data. And so what this will do is now it will take the node that's to our left and our data and call this function again. And then we'll check again. Is that null? If it's null, we could insert it there. If not, we've got to keep doing this over and over until we get to that condition. Okay, so that's if the data is less than the current node's data. So let's do if the new data is greater than the current node's data. And so that looks like this. And so in this case, what are we going to do?
Return insert node right.
We're going to go to the right. Yeah, exactly. We'll pass in our data. And so that is, actually, and then since this needs to return a Boolean, I'm going to put a return false down here at the very bottom, in case we ever get there. So that's our full private insert method. So now let's look at the public method that goes with this. And it's pretty simple. So what we're going to do for it is we're just going to say it's also a Boolean. It's from the binary search tree class. It's also named insert. And so notice they're both named insert. They have different parameters. They're also, one's public, one's private. So that sets the functions apart. But all it takes in is data, right? And so what we're going to do with that is now we can call a private method from within here. So we're just going to return our private insert method, and we're going to call it with the root node and the data we want to add. And so all that's going to do is call this function we just wrote, and it's going to specify that root node, which if you remember is like the only variable that our binary search tree keeps track of at a high level. It's just the root node. So all the public version does is it always specifies the root node is where we start, which is what we want to do. And so that makes this private method is more for our own internal like navigation of the tree as we insert, right? So nobody ever directly calls this from the public scope. It's just for us to use so we can always be sure that we know that we're referencing things within the tree. It's not just a random input that could come to us. And so that is our insert method. So let's see. How are we feeling about that? A little bit. Well, there's a few things going on here, right? There's some recursion going on. There's kind of this weird pointer to a reference thing going on. So it's okay if it doesn't just, work immediately in your mind. Remember kind of the things that we look at it conceptually, right? So when we're doing that insertion, right, in this case we start with the root, and like we come down these, right? And so that's what we're doing in that private insert function is we're navigating down and putting this exactly where it needs to go. Okay. So let's see. We only have a few minutes, so I'm going to stop us there because I think the next part will take longer. But we will pick this up on Friday, and we will finish this, and we will start AVL trees then. We'll see you Friday.